Good morning, everybody. My name is Marcin Czapla, and I work at the University of Gdansk, Faculty of Chemistry, Laboratory of Quantum Chemistry. And at the beginning, I would like to thank the organizers for the invitation and the opportunity to give a talk at such interesting conference. As you can see, you can see the title of my presentation is silicon instead of carbon, silicon amino acids. But first of all, I must to let you know that my talk will not be about the methods, equations, their improvement, etc., but about using quantum chemical methods to investigate some interesting chemical things. I hope it will be interesting. So if we say amino acid, we usually think about something like this. So the organic compound that contains a carboxyl and amino group along the side chain, which is specific for each amino acid. But as you can see in this picture, these molecules, these natural molecules, are only a small part of all amino acids that contain many non-coded compounds. Of course, if we talk about non-natural amino acids, it should be stressed that apart from this group, there are thousands of compounds that do not occur in nature and have been synthesized and modified only in laboratories. These non-coded compounds can act as intermediate products in biosynthesis, components of the bacterial cell walls, toxins, neurotransmitters, and some pharmaceuticals. And what is very interesting, the non-proteinogenic amino acids were detected in meteorites and during the probiotic experiments. So the experiments that simulated the conditions on the early Earth and tested the formation of compounds under those conditions. Among the unnatural amino acids, the silicon-containing amino acids represent very interesting class of compounds. These molecules were originally investigated over 60 years ago, but their importance have been remarked since the late 20th century, and connected, of course, with the rise of genetic technologies and proteomics. Here you can see some examples of these compounds. The silicon substitution results in increased lipophilicity, greater steric size, resistance to degradation, and of course, change in electron densities of the modified amino acids and peptides containing such improved building blocks. It is also notable that the authors of two great papers published in Chemical Society Reviews and Chemical Reviews stated that the major future goals of silicon-containing amino acids chemistry will be the synthesis of other molecules as such and further diversity in their side chains. Now, let me recall that one of the hypothetical areas of biochemistry is so-called silicon biochemistry. It is related to the possible usage of silicon atoms as the basis of alternative biochemical structures. In general, silicon properties are very similar to those of carbon atom. So this element could be used instead of carbon to form biological molecules somewhere in the universe where carbon does not appear. On the other hand, the silicon analogues of basic organic compounds are well known for over 30 years, and they are stable even at standard conditions. Because of these hypothetical considerations and the knowledge about silicon-containing amino acids, I decided to investigate the possible existence of novel silicon amino acids in which all carbon atoms, including the carbon atom from the carboxylic group, will be replaced by the silicon atom. Now, as you can see on the slide, for my project, I chose the silicon analogues of three natural amino acids, glycine, L-alanine, and L-valine. The equilibrium structures and the corresponding vibrational frequencies of all systems investigated were calculated using the MP2 method together with Dunning's basis set of triple Z equality. The electronic energies of the stationary points were refined by using QCISD method with the same basis set. I also recalculated the energies of the silicon glycine by using couple cluster CCSD parenthesis T method. And it turned out that such obtained energies differ by about 1 kcal per mole. So I decided to use QCISD also for larger system, and I believe that these energies are valid for all systems studied. The thermodynamic stability of silicon amino acids was verified through the analysis of the Gibbs free energies of the fragmentation reactions. And the Gibbs free energies were calculated by applying QCISD electronic energies together with 0-point energy corrections, thermal corrections, and entropy contributions from MP2 calculations. Due to the fact that the zwitterionic form of natural amino acids in the gas phase are significantly higher in energy than the canonical tautomers, I decided to limit my investigations to the canonical forms of silicon amino acid. And all calculations were done using Gaussian program. Now, the next 3 slides show the equilibrium structures of silicon amino acids. And here you can see silicon glycine, silicon alanine, and silicon valine. As you can see, 6 conformers were found in this case, while we have 4 isomers for silicon alanine, and the same situation in the case of silicon valine. In general, all conformers of silicon amino acids resemble those of their corresponding natural amino acids. And as you can see, the conformers differ from one another mainly by the position of the OH group located on the same or the opposite side with respect to the amino group, and by the conformation of the siloxyl group. So open, we have open geometry or closed. The relative energies are rather small, so one should consider all of the molecules studied as competitive minima. And the similar situation in the case of silicon alanine, silicon valine. It should be stressed that the similar situation is observed also in the case of the canonical forms of natural amino acids. In general, the behavior of novel silicon molecules in the gas phase is comparable to that of the canonical forms of non-modified structures. To confirm the possible existence of silicon amino acids molecules, I verified the stability of the global minima with respect to the deamination and desiloxylation reactions. And as you can see, the positive delta G values predicted for all silicon amino acids confirm their thermodynamic stability. The next slides show the infrared spectra simulated for silicon glycine, silicon alanine, and silicon valine global minima with the description of the selected peaks. So here you can see silicon glycine and, for example, OH stretching, depending of amino group, SIAA stretching, etc. Here you can see the silicon alanine spectrum, which is very similar to that of the silicon glycine. And finally, the spectrum of silicon valine. Also very similar. In general, the shape of all spectra, as well as the type of visible vibrations, can be considered as comparable to the theoretical and experimental results found for the corresponding proteinogenic amino acids. Here we have the spectra of classical L-valine. Of course, because of the presence of silicon atoms instead of the carbon atoms, we have some changes in the spectra, such as the shift of hydroxyl and amino group bands to the higher energies, and of course the presence of SIAA vibration at about 1200 wave numbers. It is notable that the similar location of SIAA stretching was obtained experimentally in the past. Finally, what is very interesting, 20 years ago, these authors published a paper in which they described spectra obtained by bombardment of silicon by hydrogen, nitrogen, and oxygen. And among the peaks they described, especially one is very interesting because mass equals 107 units corresponds to this formula. So 2 atoms of silicon, 2 oxygen atoms, and 1 nitrogen and 5 hydrogens. And it is the formula of silicon glycine, in fact. So it is possible that it was first experimental detection of silicon amino acids. To sum up, the existence of 3 silicon amino acids was postulated and preliminarily confirmed in the gas phase. All structures of silicon amino acids resemble those of their natural counterparts. 6 structural isomers were found for silicon glycine, 4 conformers were obtained for silicon alanine and silicon valine systems. The simulated infrared spectra are comparable to those of the natural amino acids, and all molecules investigated are stable against deamination and desilioxylation reactions. And it is the question, what's next? So we can modify another amino acids, another molecules, and publish it, but much more interesting is investigate the modified peptides or something like silicon peptides. So further investigation are in progress in our group, and now thank you for your
Artur, it's now time for questions.
I am waiting.
Sorry, I got a message that I was muted by the host. Excuse me. Thank you very, very much for interesting talk, and we have time for a few questions possibly. So
look on the, because some people has asked the question chat, and some of them even raise their hand. So Michał, maybe I will give you the voice, please.
Yes, I have the following question. You have switched immediately to all the carbons replaced by silicon. Have you considered studying mixed compounds with 1 carbon, 1 silicon, or 2 carbons, 1 silicon, 2 silicons, 1 carbon?
No, because the molecules with 1 silicon, 2 carbons, 2 silicon, 1 carbons, etc., are silicon-containing amino acids. And they are known for almost 60 years. So I tried to investigate something new. And
but you have shown examples where the silicon is in a completely different position. My question is about replacing, for instance, the carbon in the carbon CO2H group, bar silicon, or the carbon connected to nitrogen. Have these compounds also been studied?
No, no.
Ah, okay, thanks.
okay, are there any more questions? I cannot see. However, I would be interested from the chemical point of view, what is the effect of silicon substitution of the carbon atoms on acid-basic properties? Because these are one of the most important properties of amino acids. And I understand that there should be effect on both carboxylic group and amino group as well.
Yes,
right?
yes.
Studied that, or somebody else studied that?
The preliminary calculations concerning the acidic properties and pKa values of these compounds were done, and they revealed, but it was only preliminary investigations with semi-empirical methods and so on. But they revealed that it should be similar to those of their corresponding natural amino acids. But the additional studies are required to confirm this statement.
Okay, thank you very much. Let's thank the speaker again.